It's my great pleasure to introduce Professor Kuilin Zhang, who's an associate professor of the Department of Civil, Environmental, and Geospatial Engineering, and he's also affiliated with the Computer Science Department at Michigan Technology University, Houghton, Michigan. So we're very lucky to have him. We had some kind of out of luck. We were talking, and I thought you would invite him to give us a webinar as part of our Distinguished Professor series. You know, with COVID, actually, it turns out that some of these things are easier because we can do them remotely. Professor Zhang got his PhD from Northwestern University, and then he worked as a postdoc in the same department, Civil Engineering Department at Northwestern. Then he joined Argonne Labs as a postdoctoral appointee. And then after that, he moved to Michigan Tech, where he is right now. His research is very relevant to the things that we do. You know, he's working on smart cities, on logistics systems, connected automated vehicles, cyber physical systems, vehicular ad hoc networks, on-road vehicle testing of CAV applications, and the whole gamut. So we are really happy to have him to talk some of the projects that he has funded by NSF, DOE, DOT, MDOT, and lately from NSF Career Award. So with that, I'm gonna give the ask him to kind of talk a little bit more about himself and also his research. So I'm gonna be quiet and listen to him. So Kuilin, please go ahead and start your presentation. And thank you again for taking time for being with us.
Sure. Good afternoon, everyone, and thanks Khan and John's introductions, and thanks Khan, Dr. Khan also with the invitation for this webinar series. I'm really appreciate. Before I started, Khan also correct. So our department actually we recently just added it's called the geospatial part to our department. So previously we got a civil and environmental engineer, and it started this fall we added geospatial part to our department. And what said, maybe you guys don't know where Houghton is, but I will show. This is the map of the state of Michigan. I believe so you know where is the Detroit is here. And if it's Houghton is all the way up to the upper state of Michigan. A fun fact is driving from Houghton to Detroit is a bit longer than driving from Detroit to Washington, D.C. Today I will talk about my research on data-driven optimization-based control model for cooperative adaptive cruise control and uncertainty. And this research has been supported by an SF Career Award. We try to understand how we're using data from other vehicles and to improve the driving control of connected and automated vehicle in the real world. And the next is I will first to introduce the outline of this talk. So I'll give the background and the motivation, and then present the problem assumptions, and that will show how the data-driven optimization-based control model used in this research, and also some numerical analysis, and conclude my talk. So I think everybody know what is autonomous vehicles or self-driving driverless vehicles, cars. And it's a very popular, topic now. So basically, this one is using sensing and using this kind of onboard sensors to monitor the surrounding traffic conditions, all recognize the road and the control devices, such as expensive LiDAR, radar, camera, and GPS. And using that data and then do the computing part, right? So you want to make autonomous driving decision during computing. So first you want the perception, and then planning, and then control the vehicles. So this is the basic called autonomous vehicles, and very popular, for example, Waymo cars, and also other companies like Uber and Lyft. I know Uber and Lyft already sold that department because of some fact. So the fact is a very high cost if you want to make this kind of car, and the other is why high standard of safety requirement. So, and be honest, it's a long way to go for truly driverless. So this is why some company already, sold that department, but some company is still very passionate on these things. And maybe a potential based model for this one is called mobility as a service. For example, Waymo started his called self-driving ride service in Phoenix since 2018. However, after 2 years, they still require a safety operator in the cars. So not only the cost and safety is still a high standard to do the fully driverless because of the safety requirement during the uncertain world. Another concept is called the connected vehicles. So the connected vehicles concept actually is initiated by the US DOT, promoted by the US DOT. So basically, we installed the communication units both inside the vehicle and also on the roadside, and try to real-time communicate and share data between the vehicle to vehicle, or vehicle to infrastructure, or vehicle to everything. The objective for this connected vehicles is the benefit is we want to achieve safety. Safety is the first thing. As a traffic engineer, we think the primary objective for everything is safety, and then improve mobility and the environment. And you look at the US DOT has conducted the connected vehicle testbed. The first one is in Arbor, Michigan, back to 2012. And that's about 2,800 vehicles over there collect multi-year data. And there are also ongoing testbeds in Florida, Wyoming, and New York. I believe Dr. Ken Osby is involved with the New York testbed, and he has a lot of experience on this work. And for Michigan is very aggressive in this field. So back to 2016, and the governor of Michigan have issued a law to allow testing the self-driving car on state roads. And about the connected vehicles, here in Michigan, both build the closed testing facility, for example, an MCT, University of Michigan, and also the large one is called the American Center for Mobility, ACM in Michigan. And even in Houghton, Michigan, we are a really remote town. You just say about that one. We only have 5 signal intersections, and the Michigan DOT installed the roadside unit for all 5 intersections here in Michigan and in Houghton, Michigan. So we can conduct the research and education for this one. So the whole idea, and here how what is the future transportation system really combine not only in this autonomous vehicle or combine so-called connected vehicle together. So basically combine the connectivity and the automation technologies to together to improve the safety and the mobility and others. So a concept promoted by the US DOT and others called the cooperative driving automation. So the whole idea is using information for both the vehicle onboard sensors and also from other connected vehicles using the vehicle-to-vehicle communication, and also the instructor traffic signals, for example, the vehicle to instructor for various save applications. And the SAE also provides the standard called the J3216, define 4 classes of cooperations. From the status sharing, you just share what you observed or from your sensor, and to intent sharing, agreement seeking, and to the prescriptive cooperations. It's from these 4 classes, an increasing amount of cooperation. And for various civil, for example, if we set equal party at signal intersections, so you want the traffic signal share their information to your vehicle and how you make decisions. So it's still cooperative driving, but you share the setters. And the CACC is a cooperative adaptive cruise control. It's not just sharing, and you make the decision. Basically, every vehicle will make it called the prescriptive operations. So in the future, this transport system is not just one vehicle, automation. It's really, we care about the fleet of vehicles, not vehicle and auto instructor together. We want to build a connect and automated transportation systems. And today, my topic is how we show the information, the data from other vehicles from ourselves to make the CACC driving decisions. And back to CACC. So everybody know cruise control. I think everybody car have cruise control, right? You want to set the count speed and that you observe it, and the car driving the the constant speed. And another very popular called adaptive cruise control, ACC, and this is already appeared for a lot of cars in the market. Basically, they install a radar sensor in the vehicles, and based on radar sensor sensing data and make a decision, automatic decision, adapt to traffic the car in front of you. So CACC actually is an extension to the ACC concept. So basically, it's make automation for the longitudinal driving decisions, not for one, but consider a string of vehicles. Basically use the communication. So the communication use vehicle-to-vehicle communication. For example, DSRC or cellular V2X devices. The whole idea of the CACC is to try to improve the string stability. Especially you under the traffic flow acceleration. Basically, that's the traffic uncertainty over there. If you have this one, eventually you might lead to the kind of track jam or collision if you just consider one vehicle. So you want to improve the stability, and the whole idea, if you have the data, from the preceding vehicles, right? So if you can predict this traffic dynamics, and you can further reduce this uncertainty and make a robust driving together. And if you consider engines, vehicle dynamics, you can save energy. And if we look at CACC is not a new concept at all, basically. So back to 1990s in the Berkeley lab, so researchers already started to propose these formulations things and start to test. And recently got popular because of the connected vehicle and implemented in the real world, and also autonomous driving. And from both Europe, and they have the kind of testing, and also US DOT gave a lot of testing, and especially they test vehicles on the road. And another one from US DOE, RPRE Next Car program, which I have been involved in the past 3 years. So we look at how this safe application, particularly in CACC and eco driving to impact energy consumption. We look at this research, the most existing models, mathematical model, auto testing, they assume either free flow or the low speed situation, and not look at traffic uncertainty and test the concept. So we try to hear how to address these issues and consider how mathematically formulate this model. Because there's some closed form formulation, control formulation, but here we use called a Model Predictive Control model to formulate this problem. Because the MPC can explicitly consider the state and control constraints, because especially in the uncertainty traffic uncertainty, the vehicle is really close to each other. That's a safety constraint you have to be captured in your model. So MPC is well used concept. Is the concept here you solve a real-time online optimization problem with the model in the rolling horizon framework, but you only implement the current time slot while you keep the future in your account. Basically, you have predictions. So you have a model, you want to minimize some performance, and you have constraint on state control and safety constraint. And you can either consider you have a reference or not reference, you have a regulation called MPC, or you have predict future driving and you want tracking that problem called tracking MPC. And looking into the existing MPC-based formulations, did not try to address the traffic uncertainty, which I would talk in this talk. So basically, they consider safety constraint and also the kind of acceleration bounded, and even most of they look at the constant speed reference or low, no uncertainties. So here, so what do we think about? So we have the vehicles and how we use the real-time connected vehicle data, integrated the formulation of the MPCs and to control the vehicles, to address uncertainty. How to address uncertainty? So I said we want to prove the data-driven optimization-based controller for this one. So we try to borrow some ideas from the operations research area of decision-making and uncertainty. So to address uncertainty, there's several ways. One we call the literature called stochastic programming. So stochastic is very, very known. So you have a known distribution. distribution can be estimated from data. And then with the distribution, you try to minimize the average case, basically. So basically, this is the part of the modeling from two parts. First from data you have distribution, you infer the distribution, and then you use that one. And this is not really good for the real-time driving things, because you only consider this average case, and the other things you do not count data in real time, basically. And in the other case, maybe some distribution is not available, basically, and how to compute this one is time consuming. And to address uncertainty, another key element called key method called robust optimization. And this one really you consider worst case, right? So you only consider worst case. You don't want to use data, but you only consider worst case, the boundary conditions. And if you use this model to make the driving decision, so it can be extreme conservative, right? So while you drive things, you cannot real time, you only make the conservative decisions. So in the OI, we propose a model very popular recently. Actually, this is not a new concept called data-driven optimization or distributionally robust stochastic optimization since the last 10 years. So they really combine the two things. So you have the data, and you do not want to make every decision, but you want to connect every decisions and the robust decision together. We call this being robust, basically. So the whole idea is you find the best distribution from a certain data set. So in the decision making, so which means when you have new data, you can account the data, you find best distribution. You don't only assume distribution, but you can make decision from data. And we try to use this one to the controller. So whole idea here, from connected vehicle, you have a real-time streaming data from other vehicle because the other vehicle share the data with you, right? And the user data, you want to learn how the other vehicle performance and this the things. And then you make a construct a set of scenario. And then we will optimize decisions, driving decisions across all the things we want to find the best decision, not find one scenario from a set of scenario. And this is the whole idea we want to do, okay? So we go back to this, if we see the classic modeling process, you construct, estimate model parameter, you solve optimization model, you're done. Here we consider called data-driven modeling process or real-time modeling. So in the very beginning, you construct some initial estimates the model parameters, you solve the optimization model, and you get some new data. So you learn, you write, and use the data, you learn, you revise it, and real time, and then you solve again. And then you have some new data, and then you repeat the process. So I call this a real-time LPU or learn, predict, then optimize framework, and using streaming data. This is really true to deal with uncertainties. So what's the data? So the real-time data, it's from, we control a fleet of vehicles, the real-time from the fleet of preceding vehicles within the communication range. For example, vehicle to vehicle, for example, 300 meters for DSRC, vehicle to vehicle, or maybe longer for cellular V2X. And then we use that data in and the real-time learning how predict what will go from the front using machine learning. And then we predict how those guys to the vehicle in front of you driving. And we integrate this set of prediction to our model. So our objective is to provide a safer, smoother, and more robust CACC controller, particularly when deal with the uncertainty in traffic conditions. So, and go back to the problem statement and assumption. So here, the problem statement, problem of interest, we want to control a fleet of CAVs for only the longitudinal automated driving, decision cooperatively. We try to ensure string stability, maintain a constant time gap. We call it CACC. And we look at the traffic, traffic oscillation scenario. Look at this is a very classical fundamental diagram traffic flow. So we look at a case in this region, the congestion region, and here maybe back and forth, traffic shocks over there, and you have a lot of vehicle in front over there. That's more traffic uncertainty. We try to reduce this one. So we have some assumptions. So we assume the vehicles, can talk to each other, through vehicle to vehicle communications. And we assume that each preceding vehicles only share their current state information, that location, speed, acceleration, and whatever over there. This is defined in the current called basically safety message. So this is called status sharing cooperations. They only share the data with you, and that's how we use data in our model. And then for the controlled vehicles, so here is the really direction. So the proceeding vehicles share the data and with the control fleet, and the controlled vehicles, so they solve a MPC model, and then they ask the other vehicle in the controlled platform to make a decision. We call the prescriptive operations, and we try to maintain a constant time gap. So here, as I said, so for this vehicle, this controlled vehicle is prescriptive cooperations, and for front vehicles, so we want to use the data. So the whole idea, how we use the data from preceding vehicles and in the controller, basically. If we look at these things, so who is the vehicle really constrain the driving plateau? Actually, it's just called immediately preceding vehicle, because you do not want your leading vehicle to hit this vehicle, the safety constraints. And but if you know more traffic dynamics in front, right? So you can reduce this kind of uncertainty and improve things. So how so because this communication range you can up to like 300 meters, you can know something over there. This connected wave data will help us to reduce uncertainty or construct a set of scenario, and then the controlled fleet will be controlled, consider all kind of scenario. This is the whole idea and problem we try to solve. And as I say, we use a data-driven MPC modeling framework. Basically, the 3 steps. So first, we we'll show here the big block here. We try to use the online learning-based driving dynamics prediction using stream data from the preceding vehicles. And then we construct a set of scenarios that will be integrated real-time MPC, we call a control model here, and we solve it. And then the step 3, we only apply using the rolling horizon framework or MPC framework. We apply the current time, and then we rolling, and then we go next step. This is the whole thing. So I will discuss those blocks in detail in the next several slides. So the first one, we said we try to learn the preceding vehicles, how they drive in the next, prediction horizons, right? So we try to address the traffic uncertainty. So first one, we want to here the fleet of vehicle control, and here the preceding vehicle. For the first vehicle here in the preceding vehicle, or we call the boundary condition preceding vehicle, because we have the communication range, right? Like this vehicle in the 300 meters, in advance. And this one, we said, okay, how this guy will do, because in front of this guy, we don't know what this other vehicle behave because we don't have data. But this one can do something. So we want to estimate a set of driving states from here for each scenario of the boundary vehicle, the first vehicles, and we want to learn all the vehicle in between, how those vehicles driving. So this one, we said, because we have all the kind of data, and their speed, their gap, their acceleration, that we can real-time solve we call real-time supervised machine learning. We can real-time calibrate a car following model, for example, intelligent driver model or news model. And then we update this kind of parameter based string things. And then we conduct a simulation, real simulation during the short period. And then based on whatever this the leading vehicle driving pattern, we're predicting how the vehicle driving in all the front vehicles. And eventually what we really care about is called the immediately vehicles, basically, right? So we can predict not just one scenario, kind of a set of scenario here. And then we also, based on this driving for next prediction horizon, and we also want to solve how our controlled platform will respond for this prediction. So we saw we predict how we this vehicle will be response. So we can do several things. For example, here we saw a finite horizon optimal control problem, but we follow the a CACC, a constant time headway here, and we provide a reference. So we also saw a reference here. It's just a deterministic problem. We saw a reference here. Or you can use some closed form the CACC model fast to calculate a set of reference. So this is the whole idea how we use the data. And here we give you some more illustrate. So for the first one, so this is a typical time and space diagram over there, and this is the trajectory. And this is a trajectory. The red one is the trajectory for the controlled vehicle, and this vehicle is called the immediate preceding vehicle. And you have some vehicle in front. Whether in the rolling horizon decision-making framework or the MPC framework, we really want to say what will be in the prediction horizon. So right, we want predictive, right? The predictive is that not uncertainty over there. You have data, you can stream data here, but you don't know the future. So first, how to deal with the boundary vehicle? That's uncertain here. So as I said, so you don't know much more data here, but you know there's a bounded thing over there. This vehicle, the worst case, this guy just stuck over there, or they drive like speed limit, and in between that lot of possibilities right defined here. So you can generate a set of scenario over there, and based on these things, you want to say, how will the uncertainty in between this preceding vehicle? You still don't know that one, right? And here I said, so you can use the data for each scenario using the data, but you using the real-time machine learning, you can calibrate, how this car driving. Based on the bounded vehicle driving, you can predict how those vehicles following each other. And eventually, what you really care about is the immediately preceding vehicle. How this vehicle driving in next 5 seconds or the prediction horizon. And we do not consider one, as I said, you can take a set of driving conditions based on a set of this uncertainty here. So we construct a set of driving state for the immediately preceding vehicles. And this is the data. And I said, another thing is, what will the controlled fleet will drive? This is still uncertainty, right? So we don't know that, but for each scenario, as I said, we can either fix the horizon optimal control model to get the reference, or we can use some closed form thing to get a quick reference. This reference we follow the constant time headway. We want the way cooperate together, and you not just have one reference, you have a set of reference. So eventually, eventually after these two things, we get a set of driving state for the immediate preceding vehicles, because this vehicle constrain our plateau. And also for each controlled vehicle, we also have the predicted driving CCC driving as a reference. So this it also how we use the data. And then next, we want to how we in our formulation to use this tool data in real time, and then how to solve it. So as you said, after this step, so we will have a set of predict driving states of the immediately preceding vehicles. And this vehicle really constrain us for the next prediction horizon next 5 seconds. And we also have a predicted reference driving, CCC driving states for each controlled vehicle. We want our controlled vehicle try to close to the reference. Of course, we have the current initial states, where each controlled vehicle at the current time, where these are and where the states. So we formulated the problem called distributional robust stochastic optimization, also with distributionally robust chance constraint problem. In the next, I will show how the model formation is and how we reformulate and then eventually we can solve it. So as I said, so after the first step, we got from the real-time streaming data from the other vehicle in front. we really construct a set. This is really the two set, okay? So this is two set. So we will show how we model two set in the formulation. Basically, this two set here you can show the two set two state we really want to use. One is the location of the vehicle, and the other the speed of the vehicle, and can construct we call the uncertain set. And that in the formulation we define it called D, and this is in our formulation. So if you look here, it's a lot of equation here, but I want just to show the whole idea. So we wanted to address uncertainty in the uncertain traffic condition. We consider all the scenarios. So we call the DRSO, distributionally robust stochastic optimization, is really from the objective function. Remember, the data-driven distributionally robust stochastic optimization is a min, max, and expectation. And we want to find the we do not assume distribution. But from data, the D is the data we just construct the data set. So we want to find the best distribution in the data in our objective functions. Of course, we consider this CACC is a constant time headway policies for both the leading vehicle and following vehicles here. So we maintain the the tau h is the constant time headway, and we want the vehicles from his front vehicle, the drive speed not change too much to follow, and even for the individual vehicles, the acceleration is not change too much. It's the typical things used in the literature, and both from the leading vehicle and from following vehicle. Another thing we add here, we also construct. We said before we have the CCC reference tracking. So we for each scenario we also have the CCC driving reference. We want our the state variable here in the formulation close to the reference. The key things here, you not just have one reference, you have a set of reference. Here, so this is the objective functions. In the constraints, so you have the data, initial data, and longitudinal location state dynamics. This is the location dynamics and the velocity, the speed dynamics. And also for in the plateau, you want all the vehicle maintain a safety distance, you maintain the safety things. And we have another constraint here. Remember, we have immediately preceding vehicles, and that vehicle driving in the next prediction horizon is not just one scenario, you have a set scenario. And we want to also satisfy the constraint here, we call the distributionally robust chance constraint. So basically, you do not want a hard constraint here because you have a set of data over there. So here you want a probabilistic constraint here. And so eventually this problem called the distributionally robust stochastic optimization with distributionally robust chance constraint. And this red part is the data. So we have the data, both from the immediately preceding vehicles, also from the controlled vehicles. So this is the formulation. This formulation look at very complex, and here the key things I rewrite this at the matrix form here, but I want to address here is the data. So this distribution, we use so-called moment bound constraints in the literature. So this constraints from data really consider moments. So first you want this data as the outcome set, contain this constraint. So we will consider the distribution, we will consider that one. The case is here, they had a second moment constraint. From data, you can calculate the second moment, and using that one, you can add the constraint. Eventually, it's a semi-definite constraint here. And also consider the first moment constraint called the quadratic constraint here. And this in the distributionally robust optimization. And how to solve this problem. Even if you cannot directly solve this problem itself, but you have to reformulate the problem can be solvable. So we really reformulate the problem as a semi-definite problem. So first we deal with the DRCC, distributionally robust constraint, and based on the theorem in the literature, we reformulate it as equivalent convex constraint. I do not detail here, but this is what we do here. We also formulate the dual of the inner maximization problem as an STP, and then still hard to solve. So we use this called semidefinite relaxation technology to relax the quadratic constraint to a linear one. and then we combine the SDP problem, inner problem to the outer problem. Eventually, this is the final formulations, basically. So basically, we keep this SDR dual constraint we just said, and we keep the dual variable constraint, and the MPC state and control constraint. We still keep these things. Just look like complicated, but actually this dual and standard SDP basically is semi-definite problem, which can be solved as any SDP solver. So here we use Mosaic to solve this one, and then we get our result, and then apply in the MPC framework. So basically, so this is our formulation. And then we show some result and to show how basically we want to say what's the stability analysis of this controller. So we use NGSIM data. So we basically from NGSIM data, human driving trajectory data, we choose 3 data sets. Each one we look at if there's some oscillation over there. We find a data with 1 shock here, data set 1. We also find like 2 shock over here, and then we find another data with 3 shocks. We want to test. So for the first experiment, we say so we compare the result here, our model from the NGSIM data. We want to check what stability if our model achieves some string stability. And in the second experiment, we also compare the model performance. For example, string stability, the error, and the learning process for the preceding vehicle. Remember, we real time to learn how the preceding vehicle drive, and using here we use we can use different California model. Here we test we use a more like intelligent driver model in the literature, or we use a simplified California model, use California here. We try to see how this will impact stability here. And the third experiment, we say we also predict how the controlled vehicle drive in the next prediction around 5 seconds. So here we use both. We want to see how this one will impact our stability. We use a closed form CACC model called MIXIC, and also we said we can also solve a fixed horizon optimal control model to predict. We saw what kind of impact stability here. And in the experiment 4, so we want to see how far you want to predict, right? So we try to different prediction horizon lengths and to see how far you can predict. If you predict too long, basically you have a larger scale problem, but if too short, and maybe it's not stable. We show some result here. And the last one, we also tried what kind of the constant height we can hold for our model can still show the stability. And we show the outcome test to show the result of this model. So look at the stability analysis. So if in the literature, basically, if if the driving controller, if you follow the based California model, closed form model, basically many California should prove at we call the low pass filtering property. And if you if this kind of low pass filter, if you transform this from time domain to frequency domain, basically it's you can see the disturbance should be dampened basically. However, look at the MPC-based controller, especially you have multiple objectives, a lot of complex constraints. In some cases, maybe not always is low pass filter, but in some special case, you can prove over there. But it's very hard to prove. It's especially for our this complex model. So here we try to use empirical to find if our stability, in what kind of proper setting our model is stability. So normally in literature, we're tracking the deviations, basically the spacing deviation between the control vehicle and desired space and PC the model. So we want to say this is things should be, we maintain the safety constraint, and we do not want this thing to amplify the downstream. Basically, we want these things is to decrease or dampened. So this is the equation. So we both show the stabilities from time domain, basically we calculate spacing deviations, then we transform these things to the frequency domain, and we look at if this effect is, is downside thing, is dumping. So here is the first experiment here. Maybe it's, you cannot see the picture in that clear, but I will show here. So from 3 data set, both is the first one is human driving, so we can say it's and we plot the division to the frequency domain basically. So you can see I highlighted the 3-1 for 3 data set. This is the our model. You can see from frequency domain is decreasing, basically it's dampened. You can see from both this is the mean amplitude of the whole each individual vehicles. You can see this is really downward side from both scenario here. Data set 1 shock, data 2, and data 3 is 3 shock. So you can show all these things to show the string stable based on definitions, but human driver much better than the human driver things. So so we show the stability from this data set for us. And the second experiment, we say how the model performance based on different preceding vehicle prediction model. Because we are embedded a real-time machine learning to learn how the front vehicle driving, basically, right? And this parameter, and then we use parameter to simulate this drive in next 5 seconds or 1 second or 3 seconds. So we examine 2 models, one IDM model, just a neural model. Neural model have fewer parameters, IDM have more parameters, more complex. So from the data, we can show both IDM and neural model, the more complex model, more simpler model, and show this is dumping effect. So basically, and of course, maybe IBM for the maximum amplitude is better, but in terms of this trend, you show the same trend, even with a simple California model. The whole idea, we do not predict one scenario, right? We predict a set of scenario, basically. So this work, I'm very happy with this one. And the next one, we said we do not just predict the immediately preceding vehicles driving dynamics. We also predict how the controlled vehicles in the plateau, right? We want to say how if we other vehicle in the plateaus, control the vehicle, follow this constant time, how do we drive? What you will do in the next period, and then we will follow this guy. So as said, we use a closed form mixed signal model. Is a closed form very fast. And we can also solve a fixed horizon optimal control model, a deterministic problem over here, in the fixed horizon, and solve it. And if you say is both, string stable, basically you can see the damping effect here and how this well. Of course, if you really solve optimal things, and maybe it's better than closed form over there, but it's really show the string stable here for the 2 different model here. The first experiment here, we want to say, how long you needed for the prediction horizon, and so of course ideally without thinking about it, you look at more, and then you can reduce more uncertainty. So we choose one scenario is 1.6 second constant time headway. And the 3 traffic shock scenario. So we try, how about you look at 5 steps in head, basically 0.5 seconds, and you look at 16 steps in head, like 1.6 thing. And out of 2, you look at the 100 steps in head, basically you look at the future, you predict the future like 10 seconds. So here we showed if you only look 5 steps ahead or predict ahead like 0.5 seconds, we cannot observe the string stable here. So basically it's not decayed things. And we show until we show if you look at the 16 steps ahead, 1.6 ahead, we already show this just string stable effect. Of course, you look at more, you get more. However, if you look at the further, longer prediction horizon, that's make your problem size grow bigger, basically, right? So you have more control variable size over there. So really, you need to here we find the through our experiment things. So if so, you need the minimum preceding horizon to maintain the stability should be the same as your constant time headway here. So this is a kind of fall. The last experiment here we will show how long this constant time headway in our model you can still show the stability, right? So of course we think so. If you have a long constant time headway, normally you are more stable because you can respond basically, right? If you really short time headway, you drive really close together, that maybe you cannot respond. So here we our design is from 0.4 second, like 4 time step, all the way to 2.4 second, 24 time step, basically. So we show here, of course, in the longer one, you can see the real damping effect, basically, that's reasonable. But if you really minimize 0.4, it's not, really stable, basically, right? So 0.4 does not work here. 0.8 show some trend, basically, right? But if you go to 1.2, you already see the effect. So we try to empirically we show how this one can show this stability. Okay, so I want to give the conclusion part here. So this talk we present a data-driven optimization-based control model for safer, smoother, and more robust CCC controller, especially one dressed, under the traffic uncertainty. We use called the learn, predict, then optimize framework. So we learn the preceding vehicles, how they drive using the streaming data, basically. And then we use the learning parameter. We predict how the preceding vehicle drive in the future, or like 5 seconds, and then we also predict how the controlled vehicle for each scenario and will be driving together, follow a CCC policy. And using two things, we formulate these things to our control model, and then we solve this model to make decisions. So we combine both the status sharing from the other vehicle in front of the proton and also the controlled vehicle, the prescriptive cooperation for the CACC. And we show the stability of the model with some proper settings, basically. We have not proved it, but we show if you set the prop, within this range, we can show empirically show the string stable. And in the future, we try to consider more complex things. First, how about the preceding vehicle? It's not all the connected vehicle, but I believe in the future, maybe all the vehicle can be shared data each other, but, how the map, not really fully connected, in the front of the vehicle. That make a challenge here. And the other thing is, when we deal with the formulation, we didn't consider time delay from sensitivity or the communication latency from this thing, and how to consider that in the formulation. And the last one, we think now we really consider model in the freeway with the uninterrupted flow facilities. And how about in the future, you want to crop the driving in on arterial, basically in the interrupted flow facility, and how combine the V2I data. And here is more complex. It's not an easy problem because this kind of signal will disrupt the platons. That's more complex here. And here is something we want to do in the future. And last, I want to thank the financial support, funding support from the Career Award here, and thanks to my former PhD student, and now with Dr. Zhang, and now he work at in the urban about laboratories. And this is the paper we published in the Research part B. And thank you very much. And I look forward to your questions.
Thank you very much, Professor Zhang. And I think we can take that paper, we can send it out to the attendees after this. So we do have one question in the queue right now from Misha. So I'm gonna allow you to ask your question right now. I'm gonna unmute you. Let's see how this works. Go for it. You should be able to unmute now, Misha.
Oh. should I ask question on the Q&A or I'm waiting?
If your mic's not working, Mitcha, you can feel free to type your question in the Q&A and I'll read it out loud. So in the meantime, I guess I'll just pose a question to you, Professor Zhang. For our students who want to work on optimization and control problems for CAV performance improvement or in an adjacent area, what research problems do you want to see more students in general working on?
Sorry, I'm sorry, I missed that question. I'm sorry.
That's okay. So for our students at the C2 Smart Center who are interested in this area and want to work on optimization and control for CAV performance, or in a related area to the research you've been speaking about today, what are some like research areas that you want to see more of our students working on? Maybe like small parts of the problem.
That's a big question. So I try to answer it. Yeah. So
the time is yours.
So I try to answer that one. So what I would say here, so the traditional optimization model mostly we use for planning and not for the real-time decision making. And the CV things in the future, so we really want to real-time decision. And also the opportunity here, we have the real-time data streaming from other connected devices, right? As I said, from connected vehicles and from the roadside unit, right? All the information, how we can use this kind of data in our optimization and control model, and also the topic, very hot topic of machine learning, right? How we use data and in optimization model or control model. This is what I'm interested. I believe maybe for the center or student maybe also want to work in this area.
Okay, we got two questions in the queue. So from Dylan, one of our students, what kernel function did you use as the low pass filter?
Oh, actually, as I said, so we just use the we transform the data. We transform the time domain frequency domain. We use the Fourier transform over there. Basically from time domain to the frequency domain, basically. So this is that we use. We do not prove, or we do not use the low pass filter to prove that well. We just transform from time domain to frequency domain.
Okay, great. And Dylan, you can feel free to ask any follow-ups if you're interested. So question from Omar, comparing to other control optimization methods, how much faster is data-driven MPC in terms of CPU time and robustness? Maybe compared to adaptive dynamic programming, reinforcement learning, etc.
That's a very good question. So here, if you look at here, it's really defined the size of the problem. Okay, so in our testing, it's really related to how long is the planning horizon. As I said, if we want to do like 100 steps, you have like 10 seconds. Our experiment, we cannot calculate in real time because you cannot finish the calculation in 0.1 second. And we test, after you look at the, 2 seconds, 3 seconds over there, and then we can achieve, we can calculate in real time. And especially we also using the real-time optimization nature because we, for every time we only 0.1 time step, right? You have new data in and you calculate optimization problem. The whole idea here, we use a hard start method. So you don't need to calculate this optimization from scratch. You can use the previous solution as the initial solution, and then you calculate. And that really, at least for now, we can get compared to the current reinforcement learning or ADP or other things. Because our model is model based, and most of when ADP or reinforcement learning, it's not. Of course, you have model based, but that one we didn't compare with that, but that one is more. They do not consider the constraints basically, right? So so we didn't consider that one, but that's a good thing we should consider. And another thing. why we still use the MPC model for this one, because our decision variable is continuous, because acceleration is our continuous variable. So and we solve that one. Most from understanding, of course, from the reinforcement learning, it may be good for the state of the decision is discrete status. That's more faster. If you look at the continuous one, then the problem is will have the cross of dimensioning problem, basically, right? So we didn't use that one, but we use this one. But that's good something we need to consider. Yeah, that's a very good question.
Okay, we got time for, all right, let's see if we can squeeze in these last two. So does your objective function consider passenger comfort or factors related to passenger comfort?
Yes. So if you look at over there, so we consider, we do consider one as an objective function. Is we call the comfort we define is the scale of the acceleration, the control one. We square over there that one. So that one minimize that one. That one, that term in the literature, they define as the comfort of driving. So you want to minimize the square of the acceleration because of the control things. You don't want that to change too much. This is the what defined in the literature for the comfort.
Okay, how about the robustness of the algorithm when facing abnormal driving behavior? Are these behaviors treated as noise or not?
Yes, so that's a very good question. So really, like the front vehicle, how some guys is abnormal driving things here. So the answer, just another uncertainty, but consider here we consider uncertainty is the leading the boundary vehicle as the future traffic as uncertainty. But in the preceding vehicle, we assume they are normal. They follow some car following model. This can be a test another scenario. How about in the 300 meter, the preceding vehicle, the some vehicle have abnormal behavior, what we do. But I think this framework, our framework may consider that because we consider a set of driving scenario, right? So it's not noise. So we can say we want to, if these things, our one scenario, like one guy, driving like abnormal here, I think this model can address that one, but I didn't test that one, but that are good things to do, basically.
Okay, so we're all out of time. Huge thank you, Professor Zhang, joining us from Michigan Technological Institute, and to everyone else who joined us today. Thank you, Professor Zhang.
Thank you, Zhang, and thank you, Professor Khan, also for your invitation. I'm honored to talk.
Thank you, Kuilin. Thank you very much for a great presentation.
Mm-hmm.
And if the students have any questions, please feel free to email Professor Zhang. That'll be great. All right? Thank you.
Sure. You're welcome. Yeah. Okay. Bye-bye. Thank you very much.